Hello everybody, I will start my today another live coding session. So today I will solve this question, next permutation. So, so in this question, a permutation of an array of integers is an arrangement of its members into a sequence or linear order. For example, for array 1 to 3, the following are all the permutations of array 1 to permutations of the given array. Yeah. So that's exactly my understanding of the permutation. Yeah. The next permutation of the array of integers is the next lexicographically greater permutation of its integer. More formally, if all the permutations of the array are sorted in one container, according to their lexicographical order, then the next permutation of that array is the permutations that follows it in the sorted container. Yeah. If such arrangement is not possible, the array must be rearranged as the lowest possible order, sorted in ascending order. So let's say I have 1 to 3, and if I'm thinking 3 to 1, then the next lexicographically larger number doesn't exist. So I take 1 to 3. Okay, for example, next permutation of 1 to 3 is 1, 3, 2. Similarly, the next permutation of 2, 3, 1 is 3, 2, 1. Okay. Then whilst the next permutation of array 3 to 1 is 1 to 3, because 3 to 1 doesn't have a lexicographically larger arrangement. Okay. Given an array of integers nums, find the next permutation of nums. The replacement must be in place and use only constant extra memory. The replacement must be in place and use only constant extra memory. Okay. So since like it is impossible to, literally use the sorted container, yeah, and put all the permutations into it and sort it, and I guess the next one. Yeah, definitely is the brute force approach, but seems like it didn't accept it. Okay. So let me understand this question again. So I will given the integer array, maybe 1 to 3 or 3 to 1, and this array has at least one element. Yes. Oh, I will be given nums. Okay. So as the constraint, length of the nums is at least 1. Yep. Which means that yes. So yeah, it cannot be an empty array. So I can always find the next graphically larger element. If I'm given a single element in array, like 2, I just have to return 2. Okay. Good. And each element in the array is integer, and it should be positive numbers or 0. Okay. So let's think I'm given 0, 0, 0, 1. In that case, yeah. So, so seems like it is okay that the 0 can be the reading number. Reading 0 is accepted. So in this case, I just have to return 0, 0, 1, 0. Okay, makes sense. So I can just think of this as just like other cases, like non-zero cases. Okay, good. So let me think of this question with some examples. So if I'm given 1, 2, 3, and 2, 1, 3, obviously the brute force approach is just like I said, I use the sorted container. So I will create every possible permutation and then sort it. Then out of the sorted list, I find the given nums array. Then I reference to the next element, or maybe if it's the last element, I will take a look at the first element and return it. Yeah. So I'll say generate every possible permutation. Sort them, find given one, return the next one. Yeah. This takes a lot of time, obviously, because permutation takes the factorial of n, and sorting takes n log n, and n should be the factorial of the n. Yeah. And find the given one takes the linear scan, which is the factorial of n times n, because I have to compare each element, which has n elements, then returns the next one. Yeah, so much time. I will try to optimize this. So let's think of this from the simple one. So let's say I'm given 1, 2, 3. I mean, the array which has 1, 2, 3, number 1, 2, 3. In that case, if I sort them, it should be firstly 1, 2, 3, then 1, 3, 2, then. So the main idea is I fix this one and I fix this 2 from the in the ascending order. These are smallest numbers. Then the remaining is 3, so I put 3 here. And here, after that, I will see if I can make this number larger without affecting significant numbers. No, it's not possible. I will take a look at this. I'd like to increment this number, increase this number without affecting the significant numbers. Yes, it's possible by swapping 2 and 3. Yeah. The reason why I don't want to affect the significant numbers is that, I should say, if I'm trying to find the next number should be, okay, so simply I can say, if I make this significant number larger, it becomes much larger. So I don't affect that in that way. So I try to increment, or I should say, firstly, I try to increase this number within this range without changing 1, 2. Next, try to increase it in this range without affecting 1. Because if I find such number in this range, in that case, definitely it's, smaller than the next number, larger number, by swapping this whole range. So that's why I can say I should find the next number within the, really significant ranges as much as possible. So as I said, here I cannot find it. And here I can find it. For 2, 3, I can swap them and create 1, 3, 2. Good. Let's think 1, 3, 2 case. Changing only this range and makes the larger numbers impossible. Changing only this range is not also impossible because now it's 2, 3. And I cannot have any larger number here because all those numbers are, smaller, or smaller. So I try to increment this in this range, and yes, it's possible. So the next smallest number should come here. The weight should be 2. And after that, I sort them as 1, 3. Yeah. So it seems like I've almost found the kind of formula. So let's think more larger case and more maybe numbers with the same numbers. Like this. And let's say it's now like this. Okay, so in this case, or maybe 3 or maybe 4. Okay. If I try to increase number in this range, not possible, obviously, because this is a single number. Say I try to increase it in this range, not possible. Let me make it a bit more interesting. Let's increase add 3 here. With this 3, 3, not possible. With this 4, 3, 3, it's not possible. I can say, because this is unstrictly increasing, when going back reversely. But now I have 1, so I can swap, and I don't say swap, but I somehow take some number here, and I get the next larger number. Let's make it 2. In that case, wait a minute. I do this. Yeah. So in this case, the number which should come here, let's make it 2, should be larger than this 2. Wait a minute. So let me add one more number here. So the number which can come here, let's make it 5, should be 3. Let me make up. So far, until 5311, I can't create a larger number. But with this 4, I can create a larger number because now it has 5. Let me change it to, say, 2, 3, and 5. No, maybe 5 and 6. Yeah. In that case, I should take 5 to here, 4. Yeah. So I want the number which is larger than 4. Maybe I can use the binary search here, or maybe I can linear scan for first. Then I find this 5. So 5 should come here. And from here, it should be sorted in increasing order. Because that's the smallest number in this least least significant 4 digit. Yeah. But seems like 1156. No, sorry, 1146. Yeah. So let me rewrite it. Traverse, backward, let's say reverse 3 from tail. And then when I find some number, so I should say until while it is unstrictly increasing. If, I mean, this kind of I is found, I stop it here. Stop the traversal here. Then, so in this case here, 4, I swap this 4 with this 5. Nums I with nums j, which is larger than, nums I. Yeah. So in this case, it's 5. And I can say definitely this number exists because obviously, in the worst case, I just have to swap this previous number. Then if I swap it, the lucky thing happens. This range is already sorted. Yeah. So I reverse nums I till end. Yeah. I can say this is sorted because this number was originally sorted in a reverse way. I mean, in unstrictly descending order, because otherwise I stop it already. And here, I find the number which is larger than this 5, sorry, larger than this 4, and smallest, and swapped it. Which means that this 4 doesn't break the order, sorting order. Yeah. So let's say I have something like 5, and in this case, I traverse until here, 6. No. I traverse until this 5. And then I try to find the number which is, larger than, sorry. I try to find the number which is larger than 5, but smallest, which is 6. So I swap this 5 with 6. What happens is that they're sorted. Yeah, obviously. In descending order, still. Okay, so this works. Okay. And the edge case, I have to think is something like this. All the numbers are the same, or all the numbers are decreasing, or maybe unstrictly. So in this case, I have to return 2335. In this case, it should be 1111. So I will think how I can handle these cases. So for the first case, I start from here, and I keep traversing until the end. Yeah. So I'm thinking here, if it doesn't exist, Um, which is project? I think this number 3 step skipped. I just have to, reverse. Yeah, I think in this way I can handle it because if the given number is 1111, I traverse until the end, so I don't do any swap and reverse it. Actually, I don't have to reverse it because all the numbers are the same. Anyway, I guess the correct number. Good. And if the number is, when I track from backward, if it is increasing until the head, I don't have any place to swap. So I skip step 3. And in step 4, I reverse all the numbers. And yes, I can find it. Good. So in this way, I mean, line 50 way, I can handle the edge case. Good. Okay, so with this, so the time complexity should be O of n because I just traverse until some number and then swap, do one-time swap operation, and then reverse the given array. So in the worst case, I find such nums I as a head of the list, just like this line 45 case. In that case, the reversing, I mean, I traversed n elements, and here I reverse n elements, so it should be O of n in the worst case. For space complexity, this should be constant because I didn't use any non-extra data structure. Good. That being said, I start my implementation. So one more edge case is that I have only a single element, like this. In that case, I just have to return 3. Yeah. So let's handle it first. Don't return anything, it said. I just return. In line, okay, so otherwise, I traverse this element until the end element. And if I break from this for loop, and if such number isn't found here, yeah, let's think of that. Wait. Sorry, let's change it to while loop because it's more beautiful. No, sorry, let me go with this. So I will break, and what happens is that if I break, the I should end with I mean this I, but wait a minute. Actually, I don't use this I, which is the remaining of the for loop. So okay, let me change it. And I will keep doing it. But if I is -1, I have to break. So here, I is -1 if in case of L53 case. Otherwise, I meet, you know, this one. Yeah. Good. So where is it now? So I will do line 53 case. Or maybe let's do line 54 first. Ah, a bit annoying. Yeah. Let me go with this first. If I is -1, step 3 is skipped and reverse all the numbers. So nums to reverse. And I will return. Okay. Otherwise, find J, which me like this. And if break. And I can say J is larger than I now. And now I swap I and J index. And now swap reverse nums this one. So I would say left, right 0, so left I, and right is yep, this is it. This is just 2 pointers to reverse numbers in the range. Nums I till the end. Then that's it. Okay. Let me quickly check. So in line 67, I handle the edge case. Length nums equal 1. So if there is only a single element, I return immediately. And in line 70, I start from the last index and yep, until I is in the valid range and current I is larger than the previous number or equal, I keep moving I. And in the end, what happens is that I is -1 if I couldn't find the, pair, adjacent pair, whose left number is smaller than right number, I end up with -1. Otherwise, it meets this condition. Yep. Okay. So in line 75, I reverse the nums. I'm handling the edge case. I just have to reverse and return it. Yep. And in line 80, I find the index j, which is larger than the nums I. And out of those, I want the smallest one. So I just have to traverse j from the tail until I plus 1. And if I find such a number, I break. Yeah. And I'm pretty sure I can find such a j. Yeah. Then I swap the nums j and nums I. Okay. So I actually said I don't want to use this j as a remaining. Yeah. So I will change this implementation a bit. So again, the similar thing happens. If I couldn't find good j, it ends up with j is equal to I. Otherwise, if I find such, nums j, which is larger than nums I, it breaks with that j. So now nums j is larger than nums I and smallest out of those numbers. Good. And then in line 86, I reverse nums from index I till last index. I use the 2 pointers. Oh, and I have to move left and right pointer in the end. Okay. Let me quickly dry run my code. Firstly, for maybe this case, 3, 3. So obviously, I just will return in line 75. So this is okay. And in 1111 case, in line 77, I start I from index 3 and I keep going. And it always nums I equal nums I plus 1. Sorry, I start from here. No, I have to start from here. Yeah. Okay, and it always equal with the left adjacent number. I keep decreasing it. And in the end, it reaches -1. And I end, the while loop. And because I is -1, I reverse all the numbers. And still the same, 1, 1, 1, 1. Good. And 5, 3, 3, 2 case, I start I from this, which is index 2. And I keep moving, but I cannot find this number. Nums I is equal or larger than. Sorry, nums I is equal or larger than nums I plus 1 always. I keep going, and in the end, I reach -1. So I reverse this as 2, 3, 3, 5, and I end it. So it's okay. Good. Let me quickly check an interesting case. Let me go with this. Okay, so in this case, I start with 3 minus 2 is 1 here. And firstly, this is true in line 79. This is true. So I decreased I, and I is now 0. Now, in line 79, left half, nums I, which is 2, is not larger than or equal to 3. So I go out of this while loop, and now I is equal to 0. And here in line 88, j begins with 3 minus 1 is 2. This is while. Yep. So this while j is larger than I, yes. And nums I is larger than nums j. Yep, this is true. I decrement j. So now j becomes 1. And here, again in line 90, j is larger than I, yes. Nums I is larger than or nums I is larger than or equal to nums j. This is not true. So I go out of this while loop with j is equal to 1. And yes, line 92 is met. And in line 93, I swap 2 and 3. So now it becomes 3, 2, 1. Okay. Good. And in the end, I reverse nums I mean, index 0 to end, in this case, all the numbers with 2 pointers. So left begins with I equals 0. Sorry, left begins with I, which is 0. Right begins with n minus 1, which is 2. So I first swap in line 103, and it becomes 132. Then I move left pointer and right pointer. So left now goes to index 1, and right goes to index 1, 2. And now in line 103, left is equal to right. So I go to the while loop, and I finish. Okay. So no, this is not correct. I should not reverse from nums I. I have to reverse from nums I plus 1, because obviously nums I is the number I've just incremented. So I do this to loop in this range, and it becomes 312. Yep. So this is as expected. So this passed. Okay, good. I've covered all the lines in this code. I'm pretty confident. I will execute. Oh. Wait. I didn't fix this. Sorry, I fixed the comment, but I didn't update the code. So I've updated it. Good. Okay, accepted. So let me quickly wrap up on today's coding practice. So today I solved the question, next permutation. So in this question, I'm given an array of integer numbers, and I try to find the next permutation. Which means that out of all the permutations, I will find the permutation which is larger than the given integer, and out of those bigger permutations, I want the smallest one, which is the definition of the next permutation. If I can't find any larger permutation, I will return the smallest permutation, which means that numbers are ascending. Yeah, in ascending order. So that being said, the basic approach is that I kept, Um, yeah, the basic algorithm I used is firstly I traverse the numbers from the tail, and until I find the number pair of adjacent numbers whose right number is smaller than the left number. If I find such a number, I should, take some number which is larger than that number, but and the smallest number out of those numbers. Yeah. So like in this case 2. So I do the swapping. Then I reverse numbers following the index I've spotted out. Okay. So yeah, that's basically my approach. Okay, with this, I didn't use any extra space, but I used, and the time complexity was over linear time complexity, which was great. Okay, that being said, I finished my today's coding practice. Thank you so much. Bye.